I decided that I want to do this problem again. Not that I enjoyed it so much, but you'll see in a moment. As I said, we can arbitrarily choose the axis. So previously I chose the center of gravity as being the rotational axis. This time around I'll choose the feet for the axis. And what happens then is that this equation here will change, of course. Therefore, the lever arm for the feet, considering this rotational axis, would be 0, so I don't need this one here. The torque for the hands here would be, well, still the force of the hands times that total lever arm. So that one actually comes out to LH plus LF. Again, when I consider this one here to be LF and this one here LH, so that's a combined 1.25 meters. Positive because it's to the right. The total torque still comes out to 0, and the second torque being applied is now the weight pulling down here. So that one will be weight times the LF, the distance from the feet to the center of gravity, so times 0.84, and I should make my F a little bit nicer. And then the second equation, the force equation, still holds because it's the same three forces, and as I said, I changed my rotational axis. That's why the first equation changes. In this case, the rotational axis is on the left, and all my levers are positive, therefore, and the one that's negative here in this equation is then again the weight. Okay, the reason I do this again is because I noticed after I did it the first time, where I had to do quite some algebra, I noticed that if I do it this way, in the first equation I only have one unknown. So I can readily calculate with the first equation the force of the hands, and that would therefore come out to, again, here's some algebra, but you know, I only need one step to do that. Minus WLF, and then divide that by the total leverage. There we go. And then that equals, and when you calculate that, you will see that you come up with the same result that you did in the previous problem. And of course you need to take half of that, and again this one here itself is negative, so therefore the entire numerator is positive. Divide by a positive number, because in this case both lever arms are positive, and you will see that you come up with the same number. And then of course figuring out the force on the feet, that's the same deal as before. So as I said, the rotational axis is free for you to choose, and in this case my second way of doing it turned out to be more convenient than the first one because there's less algebra involved. This is the problem of the lunch tray, and what it says is a lunch tray is being held in one hand. As the drawing illustrates, the mass of the tray itself is 0.200 kilograms, and its center of gravity is located at the geometrical center. On the tray is a 1.00 kilogram plate of food and a 0.250 kilogram cup of coffee. Obtain the force T exerted by the thumb and the force F exerted by the four fingers. Both forces act perpendicular to the tray, which is being held parallel to the ground. So what they want to know is the force of the thumb pushing the tray down, and then the force of the four fingers holding it up. And what they have given are the weight of the tray. I know they gave us the mass, but you know, you multiply with 9.8, you come out with the weight of the tray, and the weight of the plate, and the weight of the coffee cup. They have given all lever arms to us. They say that it is in equilibrium. Let's see what they say. In one hand, center is Actually, they don't say that. They do say a lunch tray is being held in one hand, and we have to assume from the also shown from the drawing that that means that it is in rotational equilibrium. They actually don't say that. Yeah, I mean the the tray could actually rotate. They kind of leave that open, but I think we assume from the drawing and from the language too that there is rotational equilibrium, and that means that the torque is 0, and therefore we know what the torque is. Okay, learning from the last problem where I said, I can put the rotational axis anywhere I want to. I can put it right here. And that way, when I calculate the torques over here, over there, I will calculate them, but the torque here around this rotational axis comes out to 0, and therefore in my equation F doesn't figure in, and the only unknown I will have is the thumb pushing down. And therefore, yeah, and again, the rotational axis can be chosen arbitrarily anywhere, but I choose this one conveniently here because therefore I will get a 0 lever arm on this F here and eliminate one of the variables that way. Alright, so the torques therefore are going to come out as follows. The thumb pushing down, the force of the thumb pushing down, times the lever arm to the thumb, and here you would have to see that this is this 0.04 meters plus the weight of the tray, and I just noticed that I have already 2 T, so I call this TR and here TH, times the lever arm of the tray. Here is where it becomes interesting, because what is the lever arm of the tray? Well, the tray, this is the geometrical center of it, so it's at 0.2 meters measured from over here, but we need to measure it from the rotational axis that I chose to be here where the fingers are, so 0.2 minus those 0.1, so this here is 10 centimeters, 0.1 meters. Okay, this was a TR here, and then plus the weight of the plate times the lever arm of the plate, so that is going to be 0.24 minus the 0.1 here, so 14 centimeters, 0.14 meters in between. By the way, when you calculate it, might as well stay in meters, but if you really wanted to, you could do it also in centimeters. You will see that the centimeters and the meters actually cancel out later, and therefore it doesn't matter which one you used. Plus, by the way, this was a plus as well, the weight of the coffee cup, and times the lever arm of the coffee cup, and of course that is 0.28 meters, that lever arm, and that equals 0.